Hello there. So, linear momentum and impulse are two very important concepts in physics. So, today I'm going to briefly talk about linear momentum and impulse and then do a practice problem related to these two concepts. So, first let's talk about what linear momentum is. Let's say that you have an object. Suppose that its mass is m and it moves with some sort of a velocity. Okay, so this arrow on top of the symbol represents that the physical quantity is a vector quantity. So velocity is a vector, and in this case we define linear momentum by the letter P equals mass times velocity. So linear momentum P is the product of mass times the velocity of an object. Now this is a vector quantity, as you can see from the symbol, and the SI units, if we think about the SI units for linear momentum, that is kilograms meters per seconds, or we can use Newton seconds. Either units are correct as the SI units for linear momentum. Now, let's say that there's a change in the linear momentum. For example, an object, mass m, moves with some initial velocity vi, and at a later time, the object, let's say, changes direction. Now, its final velocity is different from the initial velocity. Let's assume that its mass remains the same. So in this case, you can see, since the velocity has changed, its linear momentum is a different value compared with the initial value. Okay, so if I consider this is like linear momentum initial and then this is linear momentum final, there's a difference between these two. So that difference I can say as delta P equals P final minus P initial. This symbol, what we call delta, it's a Greek letter, signifies a change. If there's a change, then we represent that by this delta symbol. So there's another way of writing this one. Since we know how to write P in terms of mass and velocity, I can write this as mv final minus mv initial. That is also a way of writing it. Okay, so we define the linear momentum and then we have the change in linear momentum. Now, the change in linear momentum, you can see now if we consider this situation, this is what happens initially and this is what happens at a later time. Now, how can this change occur? That means the velocity changes. How can that happen? For example, let's look at this one, a very common example. Let's say that you have a baseball, okay, and it comes in some velocity v initial, and then it impacts with a bat. Someone using a baseball bat hits this incoming ball. Okay, the bat goes like, the ball is coming like that. What's going to happen is that after impact, the ball will fly in this direction. Okay, let's suppose that it has a final velocity in that direction. So there's a change in the velocity. As a result, there's a change in the linear momentum of the object. So if there's a change in the linear momentum, that tells us there's a force acting during this collision between the two objects. there's a force acting during a very short time interval. And this force multiplied that short time interval, we define it as the impulse for this collision. So impulse is the second quantity that I want to define in this clip. Impulse is force multiplied by the change in time. This delta stands for the change, okay? So the force multiplied by the time. Usually this force is an average value, okay? This is an average value. So this is one way of defining impulse. But the proper way is that if we think about this collision as a function of time, let's say we have time as along the x-axis and the force along the y-axis. During this collision, what you'll see is that there's a rapid increase and a decrease of the force. Okay, so so in order to actually find the impulse, realistically, what we need to do is that we need to take an integral of the force and the time, delta t or dt. It converts into dt because we are looking at an infinitesimally small time interval. Okay, so this is, let's call that dt, and at that point, that's the force we are looking at. Okay, so this is the realistic way of defining impulse. But what we do is that instead of this changing force, we consider, okay, the force is something like, let's say, for example, an average value of this one. Okay, so we represent this as an average value, and that's what you have over here, the average value of the force. Okay. This is the more proper way of defining impulse using the integral form. But in most practical cases, if we are taking algebra-based physics, then this is the method that we use. This is also correct, which is much more, related to like calculus-based physics. We use this one. This expression we use for algebra-based physics, and this is usually used for calc-based physics. But either way, it gives you the same definition. So we talked about two things. The first one, just to summarize, we talked about linear momentum, okay, and then we talked about impulse. Impulse is also, remember, it's also a vector quantity, and the units, we can define it like this, or its integral form like that. Now if you look, the units are the same. The units of impulse and the units of linear momentum, that's the same. So we can actually make a connection between these two quantities. What we'll see is that the change in linear momentum is nothing but the impulse. Okay, so these are very important expressions, especially this one, and this one. So linear momentum, impulse, if there's a change in impulse, if there's a change in the linear momentum, that means there's an impulse. Okay, so keep these things in mind, and then let's try to do this problem. okay, where we are going to apply this concept of linear momentum. Uh, so there's a soft toy and a ball. The ball bounces, but the soft toy does not. For which case is the change in linear momentum greater? So now we know what the change in, there's another way of defining change in linear momentum. We can also call that the impulse. Impulse is also the same thing as the change in linear momentum. So you can see here, since we are dealing with vectors, and you can see all the motion is in the upward or the downward direction. So we are only interested in the y direction, not along the x direction. Okay, so since the arrow is pointing up, I'll consider up as the positive direction. So I'll write it over here, up as the positive direction, and the downward direction would be the negative direction. Okay, now I'm going to consider the soft toy first. For the soft toy, I'm going to consider the change in linear momentum. Change in linear momentum for the soft toy, let me call that T, is equal to final linear momentum minus the initial linear momentum for the toy. Now you can see over here the final linear momentum is 0 for the soft toy because it is at rest. Since the velocity is 0, even though there's mass, the linear momentum is 0 for the soft toy after it hits the surface. Then minus initial linear momentum for the soft toy. You can see, let's assume that the soft toy has a mass of m1 and the ball has a mass of m2. Okay, even though it's not given, we can assume that they have two different masses. So here then what I'll do is that you can see the direction, so the linear momentum is m1v, but look at the direction, it's pointing downward. As a result, we need to multiply that quantity by a negative sign because it's moving in the opposite direction to the direction that we defined as positive, which is the upward direction. So here I'm going to use parentheses. I'll put a minus sign, m1v, that gives me the linear momentum initial for the soft toy, and then you'll have the final answer as m1v bar, or that's the velocity. Now for the ball, if we consider the ball, the motion of the ball, again I can write the change in linear momentum, this time it's for the ball, p final prime, because now it's a different quantity, minus p initial prime. Now let's look at the final linear momentum. You can see the final linear momentum of the ball is not 0. It's bouncing up, bouncing in the upward direction, and that's the positive direction. So I can write m2, because m2 is the way I define the mass of the ball, and m1 is the mass of the soft toy. So m2 parenthesis v, because I'm going to put v, that means a positive value because the velocity is pointing in the upward direction, minus sign, I'm going to use parenthesis again, I have m2. Now let's look at here. Initially the soft toy and the ball, they are all moving in the downward direction. So it's our negative direction. So I need to put a negative sign, and then I'll put V. This negative sign, remember, this negative sign and this negative sign are because I'm using those negative signs because the linear momentum at that instance is pointing in the downward direction, and downward direction we consider as the negative direction according to this convention. Okay, so as a result, for the bouncing ball, you'll see the linear momentum would be twice m2v. Okay, now in a case where m1 equals m2, that means let's suppose that the soft toy and the ball, they have the same mass. In that case, what we can conclude is that the linear momentum change of the ball is larger than the linear momentum change of the toy. Actually, it will be twice as large as the change in the linear momentum of the soft toy. Okay, so this is something important. If you see a bouncing object, the change in the linear momentum for that bouncing object is larger compared to an object that just falls and then come to rest. So the change in linear momentum, what does that mean? There's a larger impulse. Okay, so that means impulse of the ball is larger than the impulse of the soft toy. That is also something that we can conclude. Okay, now let's try to solve a problem. So this should be a relatively simple problem. A tennis ball of mass m rebounds from a racket with the same speed v as it had initially as shown. The magnitude of the change, the magnitude of the momentum change of the ball, find the correct answer. So this figure, I'll draw the figure separately. So this shows the surface of the racket, okay, and then initially the ball comes in this direction. It has a mass m, and it comes with a speed v in that direction, and then it collides with the surface of the racket, and this is a perpendicular line I'm drawing to the surface, and then it bounces in this direction, okay, with the same speed v. So same speed v, and they have also given that this angle, that's theta, and also this angle is the same value, it's also theta. Okay, now what we are trying to do is that we are trying to find the change in the linear momentum. So you can see here I have to, since we are dealing with a vector quantity, the best way is to define our coordinate system. So I'll define the coordinate system as like this. I'll say that this is my y direction, and let's say that this is my x direction. Okay, so what I'm trying to do is that I'm trying to find the change in linear momentum, the change in linear momentum in the x direction, and the change in the linear momentum along the y direction. Okay, now if you look at the change in the linear momentum in the x direction, let's take a look at that. So we'll have the linear momentum final in the x direction minus linear momentum initial in the x direction. In the final, for the final linear momentum along the x direction, we have m v sine theta, okay, minus mv sine theta. You can see we are looking at the component of mv in this direction, and also here the component of mv in this direction. So this is the initial linear momentum component, and this would be the final linear momentum component, and they are basically equal to one another. As a result, you won't see any change in linear momentum along the x direction. How about the y direction? Delta p along the y direction. So that means p final y minus p initial y. So in the y direction, the final linear momentum is positive, okay, because that's how we define the y direction. So that would be mv cosine theta minus, because there's a minus sign, and then look at the initial linear momentum along the y direction. Actually, it's a component that is opposite to the way we define our y direction. It's like in this direction. So that means as a result, I need to put a negative sign, because if we consider this as our positive direction, then this has to be our negative direction. So as a result, I'll have mv cosine theta, and that means the minus and the minus multiplies and become plus. So then I have twice mv cosine theta as the linear momentum change along the y direction. So in the x direction I have 0, and along the y direction I have a linear momentum change of 2 times mv cosine theta. And then you can see the correct answer would be choice D, that is 2 times mv cosine theta. Okay, so I hope you learned some basics about linear momentum. Then impulse. Remember that impulse is the change in linear momentum. And then we did this very straightforward multiple choice questions. So if you like the content that I provide, please subscribe to my channel. And if you like this, please hit the like button. And if you have any questions, please comment below. I'll do my best to answer your questions and concerns. So until next time, thank you so much and have a nice day.